Welcome to my talk on inline biomass monitoring in high cell density cultivation by PDW spectroscopy. My name is Roland Hass, I'm from PDW Analytics, and I hope that I can show you some new insights into the online inline monitoring of bioprocesses. The company PDW Analytics was founded in 2013, actually as a spin-off from Potsdam University. And the aim of our company is to transfer the PDW technology, photon density phase spectroscopy, from the earlier university level into the real world as a commercial analytical instrument. So the company is the only commercial source for PDW spectrometers. And currently we are looking a lot into the development of new application areas, for example, applications in the biotech world. Our coolest current public project is called the NanoPad. It's an EU project with a lot of industrial partners, actually from the chemical industry. And here we look mainly into particle sizing, nanoparticle sizing during processes. Of course, the company is only as good as the people working for it. We are luckily having a small but very cool team to push forward the technology development. If we want to do optical spectroscopy in processes, we have a significant issue if it comes to highly concentrated dispersions, so turbid liquids. For example, here on the left graph, you see the turbidity in the y-axis, which we express as reduced scattering coefficient for a number of materials. For example, milk industry, biotech, cosmetics, and so on and so forth. And they exhibit turbidities which are way above the usually limit of conventional optical spectroscopy, where you can measure to optical densities of 3 to 5. And what happens then if you go with conventional technology into the actual concentration of these systems is that you receive signal saturation with normal standard turbidity probes, like one is shown here. So if you increase the concentration, the signal of your sensor will saturate, meaning you are insensitive to concentration changes and therefore insensitive to changes in your processes at the given process concentration. While this is different to PDW spectroscopy, you see here the same graph as before with the same data as before, and in addition in blue and red the reduced scattering coefficients obtained by PDW spectroscopy for the same wavelengths. And what we observe here, even though it's still very, very low solid content for, in this case, polystyrene particles, we see a very linear response with respect to the reduced scattering coefficient obtained by PDW spectroscopy. Now, what's the reason behind and what's a further challenge? Well, if you look into the optical world, optical density is actually an effect of both absorption and scattering of light. So if you look into this array of suspensions here on the right side, the scatterer concentration will increase in this direction, and the concentration of the absorber, here it's a dye, will increase in this direction. But the optical impression, even though each of these systems are different in their state, in their concentration, in their chemical composition, the optical expression of these systems is pretty much identical for some of them. For example, this one here looks like this sample, even though they are different in their concentration. So if you would measure attenuation with a normal conventional spectrometer, what you would get as a response is the black line, which is actually a sum of the scattering properties shown in red and the absorption properties shown in blue. So if you want to do quantitative spectroscopy in such systems, you need somehow to discriminate between scattering and absorption. And this is the main benefit of PDW spectroscopy. And here is a very brief concept. This is how it works. By PDW spectroscopy, we obtain the so-called reduced scattering coefficient, Ms prime. This coefficient is representing the characteristics of particles, cells, or droplets. And at the same time, but independent, we obtain the absorption coefficient, μA, which is a characteristic of the color or chemical composition, or sometimes the temperature of the system. Now, if we want to do also inline particle sizing, which is not the focus of today, then we can use the reduced scattering coefficient, and by Mie theory and other theories for light scattering, we can obtain particle size inline and dilution-free by PDW spectroscopy. Well, on this slide here, I would like to show you that it's indeed possible to experimentally separate absorption and scattering from each other. And this is a very easy experiment. You take a suspension, and into the suspension you add more and more dye. So you add a pigment which will cause the increase of the actual absorption coefficient, shown here in blue, while the scattering of the suspension remains constant. And vice versa, of course, you could also increase the volume fraction of the scatterer by adding more and more particles, so the scattering coefficient will increase while the absorption coefficient remains constant. With reference to this image below, on the left hand side where we increase the absorption, this is where we move across this axis, and for increasing the concentration of the scatterers, this is where we moved across this axis. Well, experimentally it's possible to separate absorption and scattering. How is this done? Experimentally, by technology, I would like to show you on the next slide. The concept behind is that we use intensity modulated laser diodes. So we have laser diodes implemented in the spectrometer, and they are modulated in their intensity, not in the wavelength. This modulation is generated by a so-called network analyzer. And what happens then is that the laser light, which is modulated, is inserted into optical fibers and guided via optical fibers into a suspension of interest. And there the light emits at the end of the fiber like a sphere of light due to multiple scattering. And the light will change its properties due to the interaction with the suspension by scattering and absorption. So, and since this is a modulation here, a so-called photon density wave is created in the suspension. And this photon density wave can be probed with a further fiber, a detection fiber. So light is coupled out from the suspension and guided back to a detector. Now the central analytical instrument is the network analyzer, and this network analyzer will look into the changes to the wave due to the interaction with the suspension. Photon density can be understood as a number of photons per volume, and then photon density wave is a modulation of the number of photons per volume. And this modulation of this wave is characteristic for the suspension, so changes in the amplitude and changes in the phase of the wave are, by theory, related to the optical coefficients, absorption coefficient and reduced scattering coefficient, based on theory, which I will not look into detail at the moment. Technically, the spectrometer itself is a box. Now you can see an image down here in comparison to a standard laptop. It has a few connections. Of course, the process probe, it's operated by 24-volt DC, and it has a USB port for computer control. The process probes, one image is shown here on the right side, are having standard diameters of 19 millimeters and 25 millimeters. For example, with the DN19 probe, we typically operate in fermenters on basis of an Ingold port with compression fitting. The probe length can be adjusted depending on the needs. The typical length is 40 centimeters. It's a purely fiber optical probe, so no electricity or whatsoever inside the probe. And the conduit length, so the length of the fibers between the instrument and the actual probe, is typically 10 meters. Now let's look into applications, and the first application which I would like to show you is the oxygenation of blood, mainly because of this being a process which is monitored with the absorption coefficient. So what has been done here, oxy and deoxygenation of an erythrocyte suspension was measured, and what we see in red is the reduced scattering coefficient as function of time, which is not changing over many hours, at least just reducing a little bit. But on the contrary, separately to the scattering at the wavelength of 657 nanometers, the absorption coefficient during the phase of the deoxygenation increases strongly and then reduces during the oxygenation phase again. So we can tune, of course, due to oxygen saturation, the optical properties of the blood, which is well known, and that can be monitored nicely by PDW spectroscopy. In addition, of course, since it's the binding of oxygen to the erythrocytes, we have a direct information of the oxygen saturation within this suspension, but I don't want to look into detail here. And in comparison to monitoring a process by absorption, of course, we can also monitor processes by scattering. Here is an example. It's the cheese formation from fresh milk, and enzyme-induced gelling by Chimex as an enzyme. So what has been done here is monitoring the process by the scattering properties. 3 different fresh milks were used with different fat concentration. We see that the milk having the greatest fat concentration also shows the highest scattering, and as function of time after adding the enzyme, we see effects in the suspension. So we have an hydrolysis period, an aggregation period, and a gelling period. The initial 2 periods, hydrolysis and aggregation, are highly reproducible. So 3 times the same milk has been treated by enzyme. But during the gelling period, because this is a 3D process within the vessel, this differs strongly. The first 2 periods are reproducible, then not. And we can also see, of course, enzyme concentration effects. If we increase the enzyme concentration, or we get significantly faster reactions. What has also been done is the application of PDW spectroscopy in algae cultivation, here mainly for inline biomass measurements. This has been a so-called mesh ultra-thin layer photobioreactor, and here PDW spectroscopy was implemented in a recirculation loop. Here Scannidesmus rubescens was cultivated over a longer period of like 20 days. And what we see here in black is the reduced scattering coefficient as function of time, and reference analytics in red and blue for cell dry weight and accumulated cell volume by sample taking. And what is nicely seen by the inline signal is that growth can be measured, cell growth and biomass growth can be measured nicely as function of time. And one can easily see effects like, for example, that the addition of nutrient solution actually lowers the slope, lowers the growth. A different way of adding nutrients would be useful here to have optimal growth of the cells. Another example is yeast cultivation. Here, real-time growth control has been implemented based on PDW spectroscopy that was done in a normal standard 6-liter fermenter. Here, the actual glucose feed, the pump speed of the glucose feed was controlled by PDW spectroscopy. How is that? Well, the scattering coefficient relates very strongly to biomass. And if an increasing scattering coefficient means increasing biomass, of course, one has an inline signal for a specific growth rate shown here in green, and if this is seen as a set point here of 0.2, then of course based on the inline signal the speed of the glucose pump can be controlled so that ideally an optimal growth is achieved. And if this is executed, we can see a nonlinear feeding protocol here for the glucose pump, and then based on this optimal growth into here 80 gram per liter of yeast in the standard fermenter in comparison to the cell dry weight of this suspension. Another example is E. coli fat batch cultivations being done at the TU Berlin. Here, without looking into details, 3 different cultivations, actually supposedly reproducible cultivations, have been executed. What we see here in blue is the absorption coefficient, and in red the reduced scattering coefficient, and then a number of further analytics. So optical density measurements based on sample taking and dilution, cell dry weight measurements, and also an approach towards inline turbidity measurement. And what we can see from these 3 cultivations that obviously they perform very, very different, with very different cell dry weights towards the batch end. And interestingly, this can be seen if one correlates the reduced scattering coefficient with the absorption coefficient. So that is not a time-dependent graph anymore. It's kind of a process trajectory. And we can very nicely see that the first batch, the B1, has a very different behavior when the optical properties are correlated to each other. So it's a time-independent indicator of how well a batch goes towards high cell cultivation. And of course, if one compares the scattering coefficient with respect to or correlates the scattering coefficient with respect to cell dry weight and compares this to different technologies, what we find is for PDW spectroscopy an inline trend which is nicely linear towards 70 to 80 gram per liter, in good agreement to the dilution-based systems, and also in good agreement to a different approach towards inline biomass sensing. If one looks a bit more into values here, we find that for inline measurements, especially at high concentrations, the PDW spectroscopy gives the best predicted biomass error towards high concentrations. And as a last example, also from the TU Berlin, here PHA production was stimulated inside Ralstonia atropha, and there very interesting effects occur, which can be measured by PDW spectroscopy. What we have here in blue is the absorption coefficient, and in red the reduced scattering coefficient for 2 repetition batches. And the trends, without looking into details, differ from each other. So here scattering goes down, absorption goes up. And by looking more into details, one can notice that the absorption gives an indicator of the residual cell dry weight estimation, while the scattering coefficient gives an indicator for the cell dry weight estimation, so the entire biomass, including the PHA. And by having those two parameters separately and inline and real time, actually process control can be induced. So the urea pulses can be controlled by a specific set point by the changing of the absorption coefficient, and the oil feed, which is needed for PHA growth, can be controlled by the reduced scattering coefficient. And by this, actually process time can be shortened, and also so the very high cell dry weight concentrations of 120 gram per liter can be obtained with a very nice PHA content and a high yield. Well, to summarize my talk, PDW spectroscopy is a calibration-free technology. It measures 2 parameters at the same time: the absorption coefficient μA, which gives an indicator about the color, the chemical composition, and the temperature. And also the reduced scattering coefficient is obtained, μS prime, which is an indicator of the particle droplet or cell characteristics. These are the absolute optical properties of the turbid liquid. We operate in the wavelength range of 400 to 1000 nanometers, and we can measure highest turbidities and concentrations well above 40 volume%. Not shown here today, but it's also feasible to do inline real-time particle sizing, and the size range we can address is between 50 nanometers and 500 micrometers. Well, this is what I wanted to tell you today. We look a lot into the chemical world, but have applications also in food, cosmetics, and biotech. And we collaborate very closely with the University of Potsdam, where we actually came from. They focus on applied and fundamental R&D, and we focus more on the commercial side of this technology. Thank you very much for your kind attention.